Hi all, welcome to part 2 of the video lecture on counters. So in the first part we saw a basic idea about what is a counter, right? And some examples also we explored, like different ways how this counter can look like. So basically it's a register only which can go through a predetermined set of states. Now what about the different types of counter, right? So on classification is like asynchronous counter and synchronous counter. It's a broad classification, right? So the difference is that if n bit counter we will be constructing using some n flip flop, right? Whether all the flip flops are controlled by a common clock or not. Accordingly, we have this classification. If all flip flops are controlled by a common clock, it is what is called as a synchronous counter. So what is a synchronous counter? Synchronous counter has its flip flops, all the flip flops, right, clocked at the same time. If the flip flops are clocked at the same time, such counter is what we can call as a synchronous counter. So as the name says, it's synchronous, right? All flip flops are working in synchronous with the clock pulse, something like that. Where in asynchronous counter, the clock of a flip flop is fed from the output of the previous flip flop. So that configuration we will see. We are not going to apply same clock pulse simultaneously to all flip flops. Instead, we will apply clock only to the first flip flop, and its output will be connected as clock to the second one. Okay, so now at this point it will be difficult for you to visualize. We will see how it is working. Okay, so asynchronous counter suffers from delay. So definitely, let me just show you the construction. So suppose I am talking about a 4-bit counter. Typically on background it will be implemented with the 4 flip flops, right? So 4 flip flop for 4-bit counting. First one, second one, third one, and fourth one. Now the other one is also like that only. 4 flip flops we needed. I am talking about asynchronous counter. Okay, this background, this flip flop, you can use D flip flop or T flip flop, anything, and that we will see from one flip flop to another how this construction will vary. And synchronous counter means this is your clock pulse, and the same clock pulse you are applying to all the, maybe this notation means the positive edge triggering, right? So this clock. So this is what we call as a synchronous 4-bit counter. Okay, flip flop can be anything, but this connection will vary, that we will see. Now let's see what is an asynchronous counter, say 4-bit counter, as per this example. So here the difference is that the actual clock we are going to apply only to the first flip flop. Okay, so these are all my flip flop. Okay, so flip flop 0, or you can number in any ways. Flip flop 1, flip flop 2, and flip flop 3. Here also we have flip flop 0, 1, 2, and 3. Now what you are going to do is this flip flop, suppose it is a D flip flop or something. Typically it is asynchronous counter. We will construct using T flip flop, but D also you can use, that we will see, but this default you can assume for T. So T flip flop in toggle mode we will connect. So that is the way we are doing, and that is somewhere everywhere, like toggle means when T is equal to 1 it will toggle, right? So anyway that technical details we will see how it is working as a counter and all that we will see. So right now something like this is what I am having. Now what I am doing is every flip flop will have an output, right? So this output, so this is output Q0, this Q1, output of flip flop 2, Q2, Q3, like that. If that is the case, this output of the first flip flop I will be applying as clock to the second one. And it is not like this common clock. Okay, similarly output of this one I will apply as clock to the second one, and here also output of this one I will apply as clock pulse to the third one. And you may be wondering how it is working, and that we have to analyze the circuit. Okay, that we will see soon. Anyway, you got an idea, right? This is how a asynchronous counter. So there is no common clock that synchronize all the flip flops. So that is why it is called asynchronous counter, and this is how the clocks are connected in this. Asynchronous counter suffers from the delay problem. Why it is so? It is because this output of the first flip flop is applied as a clock to the second one. So the second one can work only after the completion of the working of the first one. But here it is not like that. Whenever the clock is triggered, positive edge is coming, all of them are working simultaneously. So there is no delay, there is no dependency between flip-flop. But here, like a ripple carry adder, hope you remember, here you can see dependency of the second flip-flop, or the second one is being dependent on the first one, third one is dependent on the second one, fourth one is dependent on the third one, like that. So as they are depending accordingly, only after completion of the one flip-flop we can trigger the second one, right? So there will be some delay involved, and you can see that rippling effect, right? So the second one can work after the first one, so that delay is somehow it is rippling, right? So asynchronous, the same concept like what we seen in a ripple adder, ripple carry adder. So asynchronous counter suffers from the delay problem, where synchronous counter is not suffering because all of them are simultaneously triggered, right? Asynchronous counter is also referred as ripple counter. So if you are somewhere in exam, they are asking you with the name ripple counter, what they mean is asynchronous counter. So keep this very important terminology, because that delay dependence is there, right? So that is that rippling effect, like when you are putting a stone in the water, how these bubbles are forming. So that kind of a dependency is there. For the reason of the delay feeding of the clock pulse from one flip-flop to another, so we call it as a ripple counter. Yeah, that about it. And this is the one diagram I taken from some source, internet and all. Asynchronous and synchronous counter, you can visualize like that. What is synchronous counter? In both the cases, there is, basically it's a sequential circuit, right? Sequential circuit means there will be a combination circuit and there will be a feedback path, and feedback path is by means of the memory element, right? Memory element or the storage. So that will come in between anyway. So here it is mentioned, here it is not mentioned. Anyway, that is common. But what about the storage device? Storage device is nothing but the sequence of flip-flop, and those flip-flops, if we are controlled by a common clock, we can call it as a synchronous counter. If it is if there is no such common clock triggering, we can call it as an asynchronous counter. Okay, so this is from some material I got it, but anyway you got the idea, right? What is the difference? And here you can see something called as a modulus 4 2-bit asynchronous counter. Right now don't worry about this terminology. 2-bit, anyway you know this, right? 2-bit counter means on background you need 2 flip-flops, right? Yes, this is how a typical, anyway 2-bit asynchronous counter means it's made out of 2 flip-flops, that is clear. So here you can see 2 JK flip-flop, and both the JK flip-flop, the input is something connected as 1. Okay, so I think it is something like, okay, this output also you can connect. Yeah, anyway we will see how it is working those things. Okay, so this is, that's a mistake, sorry for that. Anyway, sorry, I written like asynchronous counter. It is not asynchronous counter because all the flip-flops here, they are controlled by a common clock, right? This clock I am applying here, and the same clock I am applying here also. And again, what is this bubble means? Active low, right? It will be triggered during the falling edge of the clock. Anyways, both of them are triggered by a common clock, so definitely it is a synchronous counter. Okay, synchronous counter. And what about the input JK flip-flop? Here its first one is connected in the toggle mode, and second one the input is connected as the output of the first one. Or you may do something different also. Finally, it will do counting some special sequence. It will count, and that we will see how it is done. So this is just as an example, it is given. So definitely using 2-bit, 4 states will be there, like 0 0 0 1 1 0 1 1. So accordingly what we are having is a modulo 4 counter or modulus 4 synchronous counter. Why it is synchronous? By looking at the diagram I understood that both the flip-flops are connected by a common clock. So definitely you can see that it's a synchronous counter. Okay, and 2 flip-flops are so it is a 2-bit counter, and using 2-bit 4 unique states are possible, right? So you can think of it as a modulo 4 counter. As no other information given, we are taking the default assumption, that's all. Yeah, so that about it. And now to understand this circuit in detail, you should have a very clear idea about how flip-flops are working. I mean, something which we already seen. I request all of you to watch this video. Before that, the prerequisite is you should know the flip-flop concept in detail. Anyway, this is something we already seen, just for recollecting what we learned so far. So basically flip-flop is a memory element, right? So it's a clocked sequential circuit. From latches, how it is different? Because it is clocked, right? A flip-flop circuit can maintain a binary state indefinitely until directed by an input signal to switch the state, and that how it is retaining information, those things. Flip-flops are typically bistable devices because they maintain 2 table states, set or reset, right? 0 or 1. 1. They have two outputs also, typically that Q and Q complement, one is complement of the other. And there are different applications for this flip-flop and counter, those things, and out of them, this shift register is something we already explored in our previous classes, and storage register also, storage and shift register. Now in the this set of video we will see, so first we will explore this frequency divider, how flip-flop can act as a frequency divider. This we will see first, followed by counters. Okay, so that frequency division, that concept is actually generalized to counter. Okay, so these two things we are going to see. So let's start with this one, frequency divider, how flip-flop act like that. So that concept is what we are trying to see here. So given a clock signal of frequency some f hertz, okay, how to generate another clock of frequency f by 2 hertz? So that is your that is a question. I have a clock, and what about its frequency? So it's something like that. I need a circuit. Okay, so I don't know how to implement the circuit, and what is input to my circuit? Input to my circuit is something like some clock pulse I am having, something like this. So, and it's of frequency f, and hope you know what is frequency. Frequency is what? Number of cycles per second, right? Number of cycles per second. So typically this one is what you call as a one cycle, so on particular pattern. So this pattern is actually repeating, right, over time. So this is a cycle, and typically this how many cycles are repeating per 1 second. So that is what we call as a frequency. And there is something called as time period for this. I mean the time taken to complete one cycle is what we call as a time period, typically TP. And so it's something like one cycle, right? That pattern, this particular pattern is what we call as a cycle. One cycle is completed in TP seconds, right? So the time taken to complete a cycle is what we call as the time period. So TP is what? Time period of the clock. That is nothing but the time to complete one cycle. Okay, so for one cycle I need a TP second. Then in 1 second, how many cycles will be there? TP seconds are needed for one cycle. Then in 1 second there will be 1 by TP cycles. 1 by TP cycles. 1 by TP cycles means what? Number of cycles per second. So this is frequency. So some f hertz is my frequency. So how can you relate this frequency with the time period? So frequency is nothing but 1 by time period. Hope you know this relationship in your school level itself. You are knowing it, right? So I hope so. Anyway, now you know what does it mean, time period, frequency, how these things are related to each other. That about it. Now what is my requirement is I need an output wave which is of frequency half of this. So how many cycles per unit time, right? Half cycles means you have to increase the width, then only you can reduce the number of cycles per unit time. So it will look something like this. Its time period will increase now. Okay, so what you can observe here is, so here if the time period, let it be some t seconds, right, t seconds. So this unit, then here the time period is actually this particular value. This should be some 2 times TP. If the time period is 2 times, time period we are denoting as, so this is the time period of this particular clock input, right? And the output time period, let me denote like a TP dash, and TP dash, my requirement is, it is something like a 2 times this T. Okay, so if that is the case, what I will get is the new frequency of this, frequency of this one will be 1 by time period, 1 by time period, 1 by TP dash, right? That is equal to 1 by 2T, right? Now what is here the frequency is 1 by TP, and TP is nothing but T. So this is 1 by T, right? So that this 1 by T is nothing but F. So that this will be F by 2. So what I am getting is an output waveform which is of frequency F by 2 hertz. Where the what is f? F is the input waveform frequency. Hope this idea is clear. Whenever I am applying a clock pulse which is of frequency f hertz, I need an output clock which is of frequency half of the input wave, right? That is my requirement. Can I come up with a circuit which can do this? That is a question. And one more thing, frequency and time period related opposite each other. Like when time period reduces, frequency increases, right? Time period is small means more cycles per second, so that the frequency will be high. If the waveforms are very near like this, it will be of high frequency. Here this is time period is bigger, right? Accordingly what we are having is a low frequency, and here also it's something like time period is 2 times, so the frequency will be half of the original one, right? Hope that concept is clear. Now we need a circuit that can do this, right? How can I implement it? So let me show you the circuit. It's a very, very simple circuit is what we are having. So what we will do is, we will take a T flip-flop, okay? So the fundamental T flip-flop, you know, that we will take. Okay, so this is your T input, and connect this T flip-flop in toggle mode. And you know, toggle mode means whenever T is equal to 1, it will keep on toggling. The output, it will keep on toggling, okay? And you have to apply a clock. And what is this clock? This clock you have to apply the original waveform, which you want to, some clock you are applying, right? And what is this clock? This is the input clock, which is of f hertz frequency, okay? Now clock you applied, and you just observe the output, this output, and you can see that this output is actually, it keeps on toggling. And when it is toggling, it will be toggling during rising edge of the clock. During every rising edge of the clock, it will toggle, right? And as a result, you will get, and this output you observe, and you will see that it is of 2 times this input frequency. So to understand this, let's analyze the timing diagram. Okay, so timing diagram is important for analyzing all this asynchronous circuit, okay? So we are going to see the timing diagram. So let's take the input clock to be something like this. I'm randomly drawing on clock, okay? Something like a square wave I'm trying to draw, but it looks different. Anyways, you assume it as a square wave, okay? Fine. Now, what about it? These things I'm denoting like this, because during that positive transition of the clock, the flip-flops are getting triggered, right? So in exam also you have to draw like this, and you have to convince them how it is doing that frequency division. Yeah, like this. Now you can see, so this is the input clock you applied, this particular clock, and which is of f hertz, right? And during rising edge of the clock, the particular T flip-flop will trigger, and it will do that toggling of the input. I don't know the initial value of the input, and let the initial value of the input, let it be some low value, okay? So that, you know, here I am trying to see that Q, okay, this particular output of the flip-flop. And now you can see that during that triggering, so now it will trigger, right? Trigger, it will toggle, means it will go to the opposite voltage level. Now it will continue this level until the next triggering, right? So during this triggering time only, it will change, it will do the toggling, and the toggle mode, that high level, it will retain until, I assumed that it is starting from a low voltage, okay? So that is my assumption, because clock also I started with low, so here also I am starting with low, okay? So that now during the next rising edge, it will toggle further, so it will go to low level, right? It will continue again, it will toggle further, right? Again it will toggle further. So what we are having is a toggle flip-flop that will toggle, it will change the input to 0 to 1 or 1 to 0 during the clock edge, because it is positive edge triggered clock, right? So like this. So this is your output. See, now can you observe something? What is frequency of this one? So frequency of that original one, something like this. So this is its time period, right? The time period is some t unit of time, so that its frequency is actually 1 by t. Now you can see that here the time period 2 times of this, right? It is doubling actually. So here the time period is 2t, so that its frequency will be 1 by 2t, and this 1 by, let it be f dash. 1 by 2t is nothing but 1 by t is f by 2. So you are getting the output wave which is of 2 times frequency, as the input f by 2. So it's enough. Simply connect the input clock to a T flip-flop and configure your T flip-flop in the toggle mode. That means the T input should be 1. And observe the output, and you will see that the output is nothing but a clock signal which is of, same kind of a clock signal, right? Some square wave we are getting, which is of 2 times time period of the original one, or half frequency of the original one, right? So this is how a flip-flop, single T flip-flop can work as a frequency divider. It's divided the input frequency by 2. So this is our observation. The output of the T flip-flop divides the frequency of the input clock by 2. Hence T flip-flops are also called as divide by 2. So it is dividing what? It is dividing the input clock. Okay, or frequency divide by 2 device, something like that. So it's a very, very important observation we are having. So this is what we seen when the toggle flip-flop is connected in the toggling mode. So if this is the input 1, so that this is the time periods, and f is equal to 1 by t as a frequency. This one is of 2 times the input waves time period, so that its frequency will be 1 by 2t, and that is nothing but f by 2 hertz. Okay. So the output of the T flip-flop divides the input frequency, frequency of the clock, input clock, by 2. So now clearly there is some division going on, but how do we interpret this as counting? So what we see in here, okay, I think we will discuss this in the next video, because I just want to tell you something more here. Okay, so what we see in here is a single T flip-flop connected in the toggle mode is acting like a frequency divider circuit. So the input clock, there will be a frequency for it, and that is being divided by 2 by using just a single T flip-flop. And now we will see how to cascade multiple T flip-flops so that it can divide the frequency, say by 4, 8, like that, some powers of 2. So that is a generalization we need, that we will explore in the upcoming video. And also here the topic we are discussing is counter, right? And what we see is frequency division, and how this frequency division will help the counting part. I think I can finish it over here, because we don't need much things. So what happened here is, okay, let me just conclude that also. Okay, see here I am having a T flip-flop, the input is connected like 1. We will see in detail in the next video. Okay, some clock is being applied, and you saw that the output is actually of half the input clock frequency. Okay, now another observation you need is, hope you remember how that Q is changing. The change of the Q I drawn like this, right? Initially it was 0, then it is changing to 1, and it is lasting that 1 for a long time. Whatever it is changing to 1, then again it is changing to 0, right? This transition, initially it was 0, right? Then it is changing to, let me use a different color. So if you are looking at the counter part, so it was, if you are looking at the output is 0, then output is 1, then output is 0, then output is 1, and you can see that there are only 2 states for the circuit, because there I am having just a single flip-flop, so it can be either in 0 or in 1. Only 2 states are possible. If I am having 2 flip-flop connected like that, I can think of 0 0 0 1 1 0 1 1 as the output state. So here only 2 states, and these 2 states are whenever how transition is happening during the positive edge of the clock. So some clock will be applied whenever the clock is having a transition from low to high. It will change from 0 to 1. Similarly, it will retain this 1 for some time, and whenever the next clock cycle rising edge happen, it will change from 1 to 0. So like that it will. So you can see that 0 1 some 2, right? So some kind of counting, right? 0 to 1, then 1 to 0. But this you can generalize like 0 to 1 to 2 to 3, then back to 0. So this is some kind of generalization. Now we are having just a single count flip-flop, right? So it can count 2 states, just 0 and 1. Right, and it will keep on continuing with it. So what I was saying, that it was initially 0, then it is changing to 1, then it is changing to 0, then it is changing to 1, and when that change is happening, only 2 states are there for the entire circuit, right? 0 and 1, and from 0 to 1 it is doing a transition during positive edge of the clock. Similarly, from 1 to 0 it is having a transition during next positive or rising edge of the clock, right? So you can see that, right, it's like what we are having is the divide by, this terminology is clear, right? Two device, something like that. So because it is divide in the input frequency by 2. So another name for it is divide by 2 counter also, because it can count 2 states at 0 and 1, right? Or simply it is a 1 bit counter. 1 bit counter because the counter is just having 1 bit, and that 1 bit 0 or 1, like that it is counting. Okay, equivalently you can say that it is a modulo 2 counter. Why it is modulo 2 counter? Because it is having 2 states, like that. See, all these terminologies are same, but you will get the clear picture when you see the generalization of it, like because it's just counting only 2 bits. Okay, so that you may be confused after seeing that counting from 0 to 4, 0 to 3, 0 to 7, like that you will understand the concept in general. Okay, yes, thanks for watching.